Okay, I will first of all thank the organizers, especially Manita, for the invitation. I'm going to talk about randomness in dynamical systems describing classical physical phenomena, including geophysical phenomenon, which is at the core of this workshop. And many of these systems reveal some kind of fluctuations, which are often random. So I will start with introduction. That will be my first part to fluctuating phenomena. And I will start with Brownian motion. Brownian motion was first described by botanist Robert Brown by looking through a microscope at pollen of a plant immersed in water. He found the pollen are in constant motion, as if they were living species. We will discuss analysis of Brownian motion, which illustrate a key feature of random fluctuating phenomenon, which may not have been recognized by everyone. And this is a spectral feature. So we are going to continue to consider spectral presentation of random fluctuations. And we will then touch fluctuation dissipation theorem, which is a law-like, maybe the only law-like rule characterizing fluctuating phenomenon. And the first part will be concluded by a sketch on the state of our understanding about fluctuating phenomenon. This introduction is really very personal. It's designed for a better understanding of the theory, which will be presented in the second part. Okay, let's get started. An analysis of Brownian motion. According to the equipartitioning theorem, a Brownian particle with mass m, velocity v in water with temperature T has average kinetic energy, which equals 3 kT halved. And the K is the Boltzmann's constant. And from this relation, you can derive the typical velocity of a Brownian particle, which, however, is much larger than the observed velocity. So it turns out the difference arises from the time dependence of fluctuations in the velocity, and the mean squared velocity is actually related to fluctuations on all scales, represented by a spectrum. Is there? Shall I continue?
Yes, please continue.
Yeah, it's characterized by a spectrum, big gamma of omega, and here is a sketch of this spectrum. So to the left, the frequency goes to 0 and time scale goes to infinite, and around time scale gamma tau sub d, that's the time scale of the dominant dynamics. You have some kind of spectral maximum, but the total variance, total mean square velocity is integrated, is the integral of the whole spectrum. And however, an observer can only recognize fluctuation on timescales larger than the reaction time of the eye. This is the tau sub I, indicated by the red. And so the ratio of the observed mean square velocity and the total mean square velocity is the integral of the spectrum over the entire recognizable frequency that goes from 0 to omega sub I over the integral of the spectrum over the entire range. This is approximately the range extending from 0 to the frequency of the underlying dynamics. And it turns out it's proportional to this ratio of the time scale, which is much smaller because the reaction time of the eye is much larger than the time scale of the dynamics. And if you're taking that into account, you find that the typical velocity is then comparable to the blue number given above, which is observed. So what we learned from this example is that Brownian motion, as many other fluctuating phenomena, is characterized by a continuous spectrum with a finite non-zero spectrum value at frequency omega. And so we're talking about spectrum, so we come to the spectrum representation. And here I will talk about Fourier analysis and Fourier transform. Both you have been, certainly you know, but maybe I'm not sure how much you know about the difference between the two, whether they are different. And yes, they are. Fourier analysis is designed for periodic functions. And so if you have a periodic function x, we consider here, by the way, only discrete functions, so make things simpler. And here the t is the index in time that goes from 0 to n. You have total n plus 1 times, and it is periodic, means x at time 0 equals x n, and n is in this case even, and this function can be equally described by a sum of sine and cosine functions, or sum of the exponential function weighted by ak, which is the Fourier coefficients, and that can be exactly uniquely defined from the given periodic function. And similar formula holds for an odd n. And what that means is that you can derive from that a spectrum, but this analysis holds only for periodic series, periodic functions. On the other hand, we have the Fourier transform, and Fourier transform is a mapping from a set of discrete summable series to the set of real functions defined over -½ to +½ I will explain what summable means just in a few minutes. But yeah, here this interval indicates the frequency range you can covered by this Fourier transform, and half comes from the highest frequency, which corresponds to time period of 2 time steps. And if S is summable, then the Fourier transform exists only then. And in this case, the Fourier transform is a function that takes for omega in this range the value given here below. And if the S is symmetric, you end up with a cosine Fourier transform. And this applies only to summable series. And stationary varying functions, periodic or not periodic, are not summable. So for those, you cannot apply Fourier transform directly to the stationary varying function. Okay, now the explanation what not summable means. An example, we consider a periodic function, which is just a cosine function, symmetric function, and illustrated to the right. And the Fourier transform of that, we apply the definition before, is given in the first line, and in the second line, we insert the periodic function. And then in the third line, we just rewrite it in a way that we can deal with n goes to infinite, t goes to infinite. And this is done because then you can use the orthogonality property of this cosine function. And you see that the Fourier transform is 0 at all frequency, but at frequency omega tilde, which is the frequency of the function we consider S. And at this frequency, the Fourier transform, because of the orthogonality property, is if you sum over n values, that is proportional equals n½ So if you let n goes to infinite, is infinite. This is what I meant not summable. And Fourier transform of stationary varying functions, no matter periodic or non-periodic, is not summable and hence does not exist. This is something what people sometimes forgot. Examples of summable series, an exponentially decaying autocovariant function is summable. This is then indicated to the right, that decays with increasing tau, so that if you do Fourier transform, in this case, cosine Fourier transform, the gamma is no longer a purely oscillating, purely periodic oscillation, so that you cannot apply this orthogonality rule, and so that you can show that this summation is summable, it's finite, and so that Fourier transform exists. And stationary varying non-periodic function that actually cannot be described by Fourier analysis, decomposed into discrete periodic oscillations, can have a decaying autocovariant function, and hence can possess a spectrum which is the Fourier transform of the covariant function, and this is then a continuous spectrum. So we end up with two types of spectra. One is the type A spectra of periodic functions with non-decaying autocovariant function, and the other is the type B spectra of, type A is the spectra of periodic, type B is spectra of non-periodic function with decaying autocovariant function. The difference can be seen in the properties of the spectra. For the type A spectra, the spectrum will be discrete, consists of discrete lines, each line defined by the square of the Fourier coefficient. And the omega 0 does not exist, since infinite period is not defined. If a period is infinite, half of the period is also infinite, and so on. So omega 0 does not exist. For periodic function, you don't have omega 0. Now, for the type B spectrum, the spectrum is continuous because it's the sum of cosine function. Cosine function is continuous, and you have the weights in front that doesn't change things. So at the end, you have a continuous spectrum. And you have the spectral value at frequency 0, that if you put in cosine omega equals 0, that gives you 1. So the spectrum at frequency 0 is the sum over all correlation functions, correlation function at all time x. And another important feature, the derivative of the spectrum at the origin is 0, because derivative of cosine function at the origin is 0. That means the spectrum at the frequency 0 is flat. Okay, or white if you want. Finally, it does not really make sense to talk about spectrum gamma of omega at frequency omega as being connected to a single omega, because then that implies you are considering countable frequencies, and this is not consistent with the first property that the spectrum is continuous, defined in the continuous interval, which is not countable. So you see that these two types of spectrum are distinctly different, and maybe at that point an implication to the internal waves in the ocean. You may think that because of the dispersion relations, those are periodic oscillations, but however, we don't really think so. We assume, for instance, in case of a Gary-Monk spectrum, that it's a continuous spectrum, and that implies that we think internal waves are random rather than purely periodic oscillations. And another note also that this classification here is only for stationary varying solutions. There are certainly other type of spectra which are not concern of this talk. Finally, a practical issue. In praxis, Fourier analysis is applied to all non-periodic functions. We don't care. And this it comes at the cost that the Fourier coefficients are not uniquely defined. What I meant here is illustrated here in terms of Lorentz 1963 model, where you can derive different solutions when you start from different initial condition. Below you see two solutions which looks different, but they are stationary varying, have similar characteristics, so they are equally good, so to say. And if you derive from, in this case, I produced 100 solutions, long solution, and took the last 10 million points and did Fourier analysis and get the Fourier coefficient at one frequency. And on the x-axis, we show the real component of that Fourier coefficient, and in the imaginary, y-axis, the imaginary part, what you get is actually 100 different points. So you get 100 different Fourier coefficients. That's what I meant with that you cannot uniquely define Fourier coefficient if the function is non-periodic. This non-uniqueness is addressed by statisticians using averaging osmosing techniques. So you have books of spectral analysis which describe all this method, which can be considered as a way to transform a discrete representation given by the periodogram to a continuous representation, which is crucial in the consideration of fluctuating phenomena. Okay, one slide about fluctuation dissipation theorem. There are various forms of that. Most of people working in climate know the formulation by Least, which apply actually the fluctuation dissipation theory to predict climate change by saying that the climate response to changes in external forcing is related to the fluctuation in the system before the forcing is changed. But I'm not talking about this type of formulation. I'm talking about more the original one, for instance, the one discussed by Gallen and Welton. And their formulation is based or has his role in Einstein's relation for diffusion process, which relates the dissipation of the gradient, of the concentration gradient characterized by diffusion coefficient D with random fluctuations of molecules that undergo a diffusion process, which is given on the left in terms of mean squared displacements of this fluctuation. So the significance here is to say that you see that dissipation, as described here in terms of D, is an irreversible effect. It must be regarded as fundamentally statistical in nature. It means it's always accompanied by fluctuations. And in fact, the fluctuation and dissipation are two aspects of the same thing, namely in this case, dissipation. So we are going to utilize this general idea behind the fluctuation dissipation theorem. It says that for a system in equilibrium with external forcing, in this case of diffusion, equilibrium with the surrounding temperature, for such system, anything that generates fluctuation must also damp the fluctuation. So this is idea we're going to use for the formulation of the theory later. Finally, I would like to say something about the state of our understanding of fluctuating phenomenon. I think our understanding is caught by two contradictory viewpoints. On the one hand side, we have the empiric, and we know that weather events are random. We know the movement of Brownian particle is random. So we think that evolution of a dynamical system describing physical phenomenon can be random. But on the other hand, from theoretical viewpoint, because our system describes physical phenomena, we have the governing equation for them, and those equations are generally described or formulated in as a differential equation. So for a system has a state vector bod x, and this system is governed by a set of equations in form of dx dt equals f of the bod x. And this symbol x is a component of the full state vector, and the f is a purely deterministic function of the full state vector plus some external forcing, and I call it differential forcing here. So you see that everything is deterministic, so you think that things should be deterministic. And actually, if the system is too complex, we also use stochastic consideration. Even in that case, so one example of stochastic consideration is Hosseman's stochastic climate model. And in this case, and also in all these stochastic approaches, you introduce a stochastic forcing theta, and this theta is sought to represent uncertainties arising from factors actually external to the governing equations. So this uncertainty could be related to the lack of knowledge about the underlying dynamics. So in the formulation of the differential equation above, we know not exactly how things goes, and therefore we think there's some uncertainties, or that the system has too many degrees of freedom that we cannot tackle track all of them, and therefore there are some uncertainties, as in case of Brownian motion, or that for the whether that the initial conditions is so difficult to be determined exactly, so there are some uncertainty. However, all these uncertainties are external to the dynamical system. So in principle, this stochastic consideration actually further enhance the idea that the deterministic system is actually inherently deterministic, so that the evolution should also be deterministic. With that, that's the introductory part. I would like to start a little bit also from the second part. Here, I want to start with definition of randomness. What type of randomness we are going to consider? And I'm going to give you some different approach. Namely, previous studies have been mostly concentrating on the differential forcing or the dynamical system itself. And here we think we want to do something differently. We're not considering directly the differential forcing, but the integral forcing, which is the integral of that. I will give the definition, and most importantly, I will discuss the properties of that. The thing is to show that this forcing has different properties than the differential forcing, and therefore that can make things different. And the consequence of that, this difference between differential forcing and integral forcing will be the main point of the main last point. And finally, I will give some conclusion. But before the break, I would like to give you the definition of the randomness we are going to consider. We consider only randomness in solutions of dynamical system governed by a set of equations of in the form dx dt equals f. We had that form already before, and the bod x is the full state vector of the considered system, and the symbol x is a component of the full state vector, and the f is the deterministic forcing, deterministic function of x and the constant external forcing. And so the f is our differential forcing. And this is how such a solution could look like. And a solution is said to be random when there exists a threshold big T naught such that there is no link between the solution at time t, and the solution at time t plus big T for all big T larger than p naught. That means that we're not considering solution at every time instance, the evolution of that, but considering solution at separated time, like the crosses here. And if there are no correlation between those, we say the solution is random, okay? And this has a clear implication. One implication is that because the loss of correlation, if the solution, when the solution at two separated parts time gets non-correct correlated, this means we are dealing with the solution having a decaying autocovariant function, and this is shown indicated by the blue and red here as two examples. And what we have learned is that the spectrum is then defined as cosine Fourier transform of the covariant function, and this function does exist because the decaying of the covariant function, and therefore it must be continuous. And with that, we have a spectrum that must be flat at the origin, and this value at the origin is well defined and not zero. And to see this point, actually, the not zero means comes about because the decaying, that because the correlation function at any leg tau is always mostly tends to be larger than the correlation function at any leg larger than tau. So that makes, and the maximum is at the tau equals 0. So that makes that if sum over them, they can be non-zero. And this property is a specific property, and this property is only a property of the solution, not the property of the forcing, because the autocovariant function of the forcing f consists of differences of the autocovariant function of x due to the constraints set by the differential equation dx dt equals f. Okay, this is the implication of our definition. And before the break, a few more figures indicating that we do have random solutions. The first one is a solution, the spectrum from a solution of a purely atmospheric model. They have James, they run their atmospheric model with a constant forcing and find that they have variabilities over long time scales up to 100 years. And the second plot to the right in the top panel is a spectrum derived from reanalysis. This is actually pressure difference, sea level pressure difference, characterizing then mode of variability in the atmosphere. And then lower two panels are a spectrum of current kinetic energy derived from current measurements. So all this spectrum indicates if the frequency goes to 0, this is all goes to the right. The spectrum tends to reach some flat platoon with some finite non-zero values. And you will say that actually because the length of the records are too short, we can actually not show that there is a omega 0. And this can be shown in terms of Lorentz system. This we saw that this is this solution is also non-periodic and stationary varying. And in this case, you can take longer and longer solutions so that you can show asymptotically that the solution is approaching omega 0, which is finite and non-zero. So I think I stop here for the break.
Okay, thank you, Jin-Song. We have a few minutes for questions. maybe first the students can ask again some questions. No student question. I have a student question. What is the relation between autocovariance function and the spectrum, Jin-Song?
The spectrum is a Fourier transform of autocovariant function. If I forgot to say that, sorry, that's the Fourier transform of autocovariant function. That means that you have the summation or the integral in the continuous case over all the time lags from minus infinite time lag to the plus infinite time lag. And this integral or this summation is only summable if you have decaying autocovariant function. In that case, the spectrum exists as Fourier transform of autocovariance function.
Okay, and is there another complication with finite time series then? You said that you have to do the Fourier transform from minus infinity to plus infinity.
No, that's if you have yeah, it's with a discrete time series, you can also have correlation function goes to from minus infinity to plus infinity. We're talking about, maybe I was not so clear, we're talking about functions of time. I'm just writing the whole thing in a discrete form, because the reason for that is also very important, because everything we observe or we calculate are discrete. So in the second part, I will show proof of things, everything has to be discrete. And for discrete functions, like Lorentz function, Lorentz solution of the Lorentz model, that will be discrete, and that can go from infinite, minus infinite to plus infinite time. And you can get correlation functions at the lag from minus infinite to plus infinite. So this is what I meant. With Fourier transform, you need to take all of them into account. And that is sometimes problematic if you can do Fourier transform of the solution itself. That's most people tend to do, but this has the problem that actually this Fourier transform does not exist, because this stationary varying thing that is not summable. So you cannot first, if you have a solution, you cannot first do the Fourier transform of the solution and then get from the solution the spectrum, do squared and get spectrum. You have to do first the autocorrelation function, which is decaying, and therefore it is the Fourier transform exists, and then you can define spectrum that way.